Modern cipher vulnerabilities are rarely found by staring at a single encrypted message. Instead, cryptanalysts look at the mathematical distance between two carefully chosen messages. This approach is called differential cryptanalysis. Linear cryptanalysis tries to track single bits of data. Differential cryptanalysis tracks pairs. It is a chosen plaintext attack. To execute it, an attacker takes a massive number of plaintext pairs and encrypts all of them using the same target key. The core metric is the input difference, calculated by taking the bitwise XOR of two plaintexts, denoted as X prime. Fixed across thousands of pairs, they pass through the cipher, mutating into ciphertexts Y and Y star. We XOR these to find the output difference, Y prime. By tracking exactly how these specifically chosen differences propagate through the mathematical chaos of a cipher, we can extract the hidden key bits. To understand how a difference propagates, we have to look at the microscopic level of the cipher, the individual substitution box, or S-box. S-boxes are explicitly designed to be nonlinear and produce seemingly random outputs, but their XOR propagation behavior is highly predictable and non-uniform. This is Table 4.3 from the text, displaying the raw data of an S-box when we provide a specific input XOR of 1011. Look at the last column, Y prime. This tracks the resulting output XORs for that 1011 input across every possible pair combination. Out of 16 possible output variations, only 5 actually occur, and a single output, 0010, appears exactly 8 times. Half the time this S-box processes a 1011 difference, it spits out a 0010 difference. Cryptanalysts calculate these anomalies for every single possible input and output combination, mapping them out on a master grid. This grid is the difference distribution table. It maps the comprehensive biases of the S-box. The y-axis, A prime, represents the input XOR. The x-axis, B prime, represents the output XOR. We can trace our previous example here. If we locate input hex B, which is 1011, and output hex 2, which is 0010, we find that same intersection value of 8. We call this the propagation ratio. It is the conditional probability that a specific output XOR will occur, given a specific input XOR. For our specific example, 8 occurrences divided by the 16 possible states equals a strict probability of 1/2. S-boxes are entirely transparent to statistical analyses. They leak predictable biases, and those biases provide the exact mathematical foothold needed to break the cipher. We now take that single S-box anomaly and scale it up to an entire substitution permutation network. This diagram illustrates a differential trail. It works by chaining those highly probable S-box differentials together across consecutive rounds of encryption. An initial input XOR enters the first round and passes through this specific S-box, S21. The output difference from that S-box is then scattered by the permutation layer. Those bits feed directly into specific active S-boxes in the second and third rounds. To calculate the viability of this path, analysts make a crucial mathematical assumption. The propagation ratios of S-boxes in different rounds are treated as independent probabilities. To find the total probability that a difference will successfully follow the entire trail, we simply multiply the propagation ratios of all the active S-boxes together. This equation shows the exact probability calculation for the 3-round trail we just mapped. The math gives us a precise result. In 27 out of 1,024 cases, this exact XOR pattern will successfully survive 3 full rounds of encryption intact. By stacking these microscopic S-box biases, attackers can predict the internal state of the cipher right before the final round. This algorithm details the execution. It outlines how to use the differential trail to extract the final key bits. The attack requires a massive data set of tuples, pairings of the chosen plaintexts and their resulting ciphertexts. The core mechanism of the algorithm is a filtering operation. Tuples not matching the expected output XOR conditions are classified as random noise and discarded. The rare tuples that successfully match are called right pairs, proving they followed our predicted mathematical trail. The algorithm tests every candidate final round subkey against these right pairs. When a subkey yields the expected intermediate XOR, its counter increments. Finally, the subkey with the highest count is mathematically guaranteed to be the correct key. For this extraction to succeed, the total volume of ciphertext pairs required must be strictly proportional to the inverse of the trail's probability. Differential cryptanalysis turns encryption into a statistical filtering problem. It proves that minor structural biases, when chained together, generate enough data to unravel an entire multi-round cipher.